Hello all, welcome back. As part of intermediate DSA module 2, we will see time complexity today. We'll start with log basics and iteration problems, comparing the iterations using graph, time complexity and what is big O. We'll see common problem faced by any developer, that is time limit exceeded, how to overcome that, and what is the importance of constraints from the given question while solving any DSA problem. Okay, let's get start with logarithms and basics. So whenever I write log a base b, in general that means to what power I should raise b to get the value of a. So log a base b means to what power that I raise my b so that I'll get a value of a. So we'll see that. Let's take some examples. We have log 64 base 2. 64 can be written as 2 into 2 into 2 into 2 into 2 into 2, or else 2 power 6, which is also written as 2 power x, because 2 is raised to some power so that I can get 64. So from this 2 I can write x is equal to 6. That means log 64 base 2 is 6. Similarly, 32 can be written as 2 power 5, and I am looking something 2 to the power x, which is a representation of 32 base 2 power 5. From this x is equal to 5. Now something like you have log 10 base 2, but if you see 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 is 16. You don't see anywhere 2 power something giving rise to 10. In such scenarios, what you should take, if you consider from this both, right, 10 is somewhere between 2 power 3 to 2 power 4. So can I write x is something, 2 power something, some 3.xx, right? That means log 10 base 2 is equal to 3 point something. If I ignore the decimal point, it is approximated to 3. So you have to take the floor of it. Similarly, 40 is between 2 power 5 32 and 2 power 6 64. So I can write log 40 base 2 is 5 point something. If I ignore this, this is approximated to 5. And we discussed so far log b base a means raising the power of a so that we'll get b. Now from the definition I can take a power x is equal to a power b, x is equal to b. Similarly, 5 power x something is equal to 1. The only power 5 to give 1 is 5 power 0. So x is equal to 0 in this case. So any log 1 base, any base is 0. Right? Okay, how this logarithm, concept of mathematics is useful in DSA. Let's see. Given a positive integer n, the question is how many times do we need to divide it by 2 until it reaches n. So you have a positive integer n, you do series of divisions by 2, right? How many times shall I do this until I get the answer is 1, right? We'll take an example, we'll solve an example. From the observations, we'll come to a conclusion, similarly how we did in the last class. Let's take n equal to 100. So you take 100. For the first time, if you divide it by 2, it is 50. Again you divide it by 2, it is 25. Divide it by 2, you cannot write 12.5, you have to write 12. I think everyone is aware of this basic mathematical operations in coding. And again divided by 2, 6. divided by 2 is 3, divided by 2 is 1. So if you see how many times did I divide by 2? 1, 2, 3, 4, 5, 6. If I draw some observations, from the method I followed. So I had n, I made it n by 2. In the next time I made it n by 2 that is 2 square. Next time I am dividing the whole value by, sorry, it's not 3, it's 2 power 3. Dash dash dash, somewhere around n by 2 power k, that will be sure equal to 1, right? That means my n by 2 power k is equal to 1. Applying log, okay, I can write n equal to 2 power k first. Applying log on both sides, log n, right, base 2 is equal to log 2 power k base 2. As we discussed so far, log 2 power k base 2, that is log a power b base a is b only. That means it's equal to k. So log n base 2 equal to k, right? What is this? K is number of times I am dividing here. If you observe the series that we generated, I am dividing it k times to get 1. So to get the number, you just apply the logarithm for a given whole number. So you have a positive integer n, how many times you divide it by 2 until you reach 1. This is a loop that you are trying to solve, the number of iterations, how many iterations you need. For every iteration, if you divide it by some number, is logarithm of that number, right? Cool. Yeah. Now we will see some iterations problems. We'll see how to find the number of iterations for the given loops. I have one question here. N is greater than 0, I equal to n, while I is greater than 1. While I is greater than 1, I am dividing I equal to I by 2. So this is as usual. If you take example n equal to 20, you have 20, divided it to 10, again divided to 5, divided to 1. This is common division problem that we see. That means log 20 base 2, which is approximately equal to 4. Or else can I say number of iterations is log n base 2. This is number of iterations. I am trying to see first number of iterations. Please don't get confused with time complexity. First I am only trying to solve number of iterations as we did it in the last class, but now we are doing with some logarithmic problems. I have one more example. Similarly, take n equal to 20, right? Now what I am doing, I am taking I equal to 1, and for every iteration I am multiplying it with 2. So this is not division, it's a multiplication. So first time I am multiplying with 2, next time I am multiplying again with 2, third time again I am multiplying with 18, lastly I am multiplying it with 2 again. It is 60. If I any further multiply, it becomes 32, which is greater than n. That is not needed. So it's the same one. If you observe reverse also, you are trying to reach to 1. So some 2 power k is trying to reach n. So you wanted to know how many iterations it is made. It is log n base 2. One more shortcut. If you have iterations in the form of division, or your iteration is getting multiplied, right, you can see if there is any log n iterations are happening. That's a possibility. With different combinations the iterations will change, but if there is any division or any multiplication, the first thought you can go for is whether is there any logarithm involved, right? We'll get to the next question. The next question, I have I equal to I into 2. I'll confirm, is it logarithmic? No. Blindly we shouldn't go for it. That's a hint only. We have to still check I can take n equal to 20 and I equal to 0. If you see, first time it's 0, next time multiplied by 2 again 0, next time multiplied with 2 again 0, next time multiplied with 2 again 0. So the iterations are infinity. It's an infinite loop. Okay, more or less we have to always check. Even there is a multiplication, I couldn't go directly blindly for log n. I have to see from wherever it is starting. Cool. We'll see one more question, an interesting question, which is having a 2 for loops. If you have such multiple for loops, I would suggest drawing a iterations table would help. Take all the parameters that is affecting your iterations you feel, right? So if you observe, for the first time when I equal to 1, my j is actually running from 1 to n. So number of iterations when I equal to 1, that j is making, the inner loop is making n iterations. Similarly, when I equal to 2, my inner loop again it is starting from 1 and running till n, that's an n iterations. This trend continues till I equal to 30, 1n, so the iterations is n. Now you have to see carefully, you have figured out the number of iterations for each I value for the external loop. So this is the total number of iterations that I see 10 times into n, because my I is ranging from 1 to 10 and for each iteration j is making n iterations. So the iterations is 10n, right? Clear? I'll talk about order of n, time complexity little later, but I'm just focusing on the iterations. Similarly, if you try to solve this problem, for I equal to 1, again my j is making 1 to n, so n iterations. I is raising starting from 1 and till running till n, so every iteration of I, j is making n iterations till n, right? Till n, how many? N times n, right? So the iterations are n cross n. So outer loop is running n times, where inner loop, for each outer loop it is running n times. So this is the number of iterations. Similarly, if I go for the third one, where I is starting from n and I is less than or equal to n, I think both are same. Yeah, both are same. What I will do is I'll quickly change this question. I'll quickly change this to j equal to j is to 2. Yeah, let's make this interesting. So my outer loop when I is 1, j is 1, 2, next time it's 4, right? How many times it is running? Right, this we discussed. There is a inner loop which is starting from 1 and it is making multiples of 2. The iterations would be log n base 2. Similarly, for I equal to 2, same log n base 2, right? And finally n terms I see where this is also log n base 2. So every iteration is log n base 2, but total number of outer iterations is n. So iterations I would count is n into log n base 2. Cool. Now we'll see one more example where my I is starting from 1 and it is reaching till n, and my j inner loop is starting from 1 and it is reaching till 2 power I. Whenever I say 2 power I, it's a power, right? Let's see. When I is 1, my j is starting from 1 until 2 power 1, right? So 1, 2 power 1 is 1. 2 power 1 is 2. So number of iterations is 2. Similarly, when I is 2, j is starting from 1, 2, 3, 4 till 2 power 2 or 4 iterations. When I equal to 3, again 1, 2, dash, 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 right, till 2 power 3 is 8. number of iterations is 12. So if it is I equal to 4, I see 1, 2, 3, 4 till 2 power n, right? So this is 2 power 1, 2 power 2, 2 power 3, dash 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 2 power n. So if you see my sum of iterations, okay, my sum of iterations are in geometric progression. That was a previous class that we discussed. So where a equal to 2, I can see from the series r equal to 2. My sum would be 2 into 2 power n minus 1 by 2 minus 1, which is equal to 2 into 2 power n minus 1. Yeah, so iterations are 2 into 2 power n minus 1. You can ask me, why didn't we consider the outer loop n? Actually we did. We deliberately resolved for each I how many times j is iterating. That means we already included I. In earlier cases it's all equal, so instead of adding one by one line, I wrote n into multiplication of log n base 2. Yeah, that's it for now. In the next class we will see how we compare algorithms using graphs and big O notation.